Assalamualaikum and good day everyone. My name is Muhammad Aizat bin Muhammad Sulaiman and our group members are Farahanan, Safwan Naim, Nurul Huda, Muhammad Amin and Muhammad Afiq Zulhilmi. Our project title is Monitoring and Automation of Carbon Dioxide and Humidity Control via Mobile Application for Oyster Mushroom Cultivation. This project is fully supported by University College Tati short-term grant. Mushroom cultivation is a growing global industry projected to exceed 10 million tons annually, requires tightly controlled environmental conditions such as humidity and CO2 to ensure successful yields. Traditional open space farming methods are vulnerable to climate fluctuation, pests, and contamination, making consistent growth difficult. Controlled environment chambers provide a stable, sterile space for cultivation, leading to improved productivity and quality. Recent studies highlight the benefit of automation in mushroom farming, including reduced manual labor, minimized human error, and enhanced environmental regulation. Systems using sensors, microcontrollers, and technologies like Arduino and machine learning can efficiently maintain ideal growth conditions. For the first objective is to design and implement an automated environmental control system for oyster mushroom cultivation that regulates carbon dioxide and humidity levels within a fruiting chamber. For the second one, to provide real-life monitoring system through the data collection from the sensors to be displayed on IoT system. For the third one is to evaluate the effectiveness of the system in maintaining optimal environmental conditions. Figure 1 shows mushroom chamber system approach. Blink is a low-code IoT platform that enables users to quickly build and manage connected devices and applications. The Blink is connected to contactless water level sensor, humidity sensor, CO2 sensor, LCD, intake and exhaust fan, and water pump. Figure 2 shows the flowchart of the program. Start, read the humidity level. Is the humidity level between 80% to 90%? If yes, turn off intake fan and turn off the water pump. Proceed to read CO2 level. If no, turn on the intake fan and turn on the water pump and proceed to read the CO2 level. Read the CO2 level. Is CO2 level below 800 ppm? If yes, turn off the exhaust fan. If no, turn on the exhaust fan and display humidity level and CO2 levels. End of the program. Figure 3 and 4 show mushroom chamber design and finished product. The mushroom chamber is purposefully designed to create a stable and optimized environment. Internally, the setup includes contactless water level sensor, humidity sensor, CO2 sensor, intake and exhaust fan. For the result, the condition of intake fan and water pump. Humidity level below 80%. The intake fan is turned on to blow air over the water curtain, which is formed by activated water pump. This process releases cool, moist air into the chamber, increasing the humidity level. Humidity level over 90%. Both the intake fan and water pump are turned off. For the condition of exhaust fan, CO2 level below 800 ppm, the exhaust fan will turn off. CO2 level over 800 ppm, the exhaust fan will turn to expel excessive CO2. This action maintains CO2 concentration below 800 ppm by facilitating fresh air exchange for supporting healthy mushroom development. For the humidity result, Figure 6 shows humidity data was collected over 10 hours, showing an increase from 82.3% of humidity level with the system effectively maintaining levels below 90%, thus demonstrating its ability to regulate humidity and prevent excessive buildup. For the CO2 result, Figure 7 shows that CO2 level initially high were effectively reduced and maintained below 800 ppm, demonstrating the system's ability to manage and expel excess CO2 and thus ensuring safe air quality. Sensor reliability result. Table 3 shows that humidity was maintained at an average of 86.17% with standard deviation of 2.69, while Table 4 indicates a CO2 average of 680 ppm and a standard deviation of 7.29. The lower standard deviation for humidity suggests it is more stable and easier to control than CO2. Nonetheless, CO2 levels remain below 800 ppm, indicating effective environmental regulation by the system. Overall, the control mechanism successfully maintained optimal conditions for oyster mushroom cultivation. Conclusion. To conclude this presentation, the system effectively automates the regulation of key environmental parameters, humidity and CO2, ensuring optimal conditions for oyster mushroom cultivation without requiring manual intervention. Automation minimizes the impact of external factors such as climate variation, human error, and pests, thereby improving reliability and reducing the risk of contamination or crop failure. It can be concluded that the integration of sensors and real-time data monitoring enables precise control of environmental conditions, contributing to consistent and healthy fruiting cycle. In closing, the developed chamber represents a significant step forward in the modernization and optimization of specialized crop cultivation, particularly for mushroom. This mushroom chamber also improving efficiency and yield consistency. The following references were used to support the content presented, ensuring the accuracy, credibility, and relevance of the information discussed throughout this presentation. I will give the title of relevant article. 1. Automation and monitoring system for mushroom cultivation using mobile application and ESP32. Number 2. Nutritional qualities and antioxidant activity of 3 edible oyster mushroom. Number 3. Onion juice waste for production of Pleurotus, Sajo-Kaju and Pectinaceae. Number 4. Pilot scale bioconversion of rice and sunflower agro residues into medicinal mushroom and lacase enzyme through solid-state fermentation with Ganoderma lucidum. Number 5. Mushroom cultivation technology for commercial production. Number 6. Prototype system of temperature and humidity automatic in oyster mushroom cultivation using Arduino Uno. Number 7. Technologies for beneficial microorganism inocula used as biofertilizers. Number 8. semi-automated mushroom cultivation house using IoT. Number 9, design of monitoring system temperature and humidity using DHT22 sensor and NRF24L01 based on Arduino. Number 10, fungal biocomposite, how process engineering affect composition and properties. And last one, a smart automated and scalable indoor harvesting system for gourmet mushroom. Thank you for taking the time to watch this presentation. I truly appreciate your attention and interest in the topic. I hope the insights shared were clear, meaningful, and sparked new ideas or reflection. This project is fully supported by University College Tati short-term grant.